last week. Do you remember? Or yeah, I guess not this earlier this week about evaluations. Good news. You can see this class is 60% of the way there. So there are two different evaluations that I am asking you to do. This is the one sponsored by the university. And if we can get at least 23 of you guys out of the 25 to complete this, everybody gets a point of extra credit. That was one of my deals. The other evaluation, you should have received a Qualtrics survey invitation via email. And if you complete that separate evaluation, which has more specific questions that are more useful to me, I will also give you a point of extra credit. So up to 2 points available for participating in a democracy. The university evaluations are not terribly helpful usually because they're very unspecific, but they are required for evaluation purposes. So I'd like to get a good representative sample of everybody. So you are beating the other class, as you can see. So I pointed this out to them. We'll see if they accept the challenge. We'll see who wins. All right. Let me move off of that one. Any homework questions? Homework 6 is available. Fun with invariance. I have started grading your homework 5s, and I'll let you know when those are done, hopefully within the next week. And homework 5, just like homework 3, you do get to do a revision. So you can fix whatever is missing, and I'll give you your points back, but that's not due until the end of finals week. And if you look at your work and you're like, you know what, I'm happy, I don't need my last point, and you don't want to revise it, that's fine with me too. I can understand. Jordan has a question. Can you go over how to free factor variances and means again? Sure, I can. Let me pull up an example that has things that are free versus fixed. Maybe we'll do you want to, Jordan, do you want to do the WLSMV version or the MLR version? Do you have a preference to answer that question? So I'll open whichever one. No preference. Okay. Well, the code is very much the same either way, so we'll do, it's a multiple group example that you guys are doing, so I'll pull up 7A. Okay. So this was example 7A. We're looking at multiple group invariance. So these would be independent groups like in your homework. And this is a CFA model, so a linear relationship between the trait and the factor. So that means that you have a grouping variable here that you would have to identify. And this is the configural model in which all of the item parameters are estimated separately per group. And for identification purposes, the factor variance is fixed to 1 in both groups and the factor mean is fixed to 0. So at this point, cough, cough, homework question, the two groups are not on the same scale. So if I were to look at the loadings or the intercepts or anything else and try to make some sort of comparison about how one group is relative to the other, that would not make sense because at this point, each factor is identified separately. So what 0 means is not the same across groups. What 0 means is the average trait level in that group. What 1 means is the amount of variance in that group. So we can't talk about how the parameters of the model relate to each other across groups until they're linked together, which happens at the metric stage. So model 2 on page 4 of example 7A, then the reference group, that's the one that is designated as the model here. Its factor variance stays at 1 and its factor mean stays at 0. But in the alternative group, so the model other group, which I think in your homework would be like model student, I think, are there the alternative group if I remember correctly. Once you add the constraint to the loadings that forces the loadings to be the same between groups, in the alternative group, you would then free the factor variance. So those two pieces of code that I've highlighted, L1 to L9, which is the loading labels that force the constraints across groups, and then the factor variance being estimated, those go concurrently. That way you're only constraining the loadings and not constraining the variance. And the factor mean at this stage is still fixed to 0 because you haven't done anything for constraints on the intercepts. So the intercept and mean side of the model are still on different scales at this point. It's only the loadings and factor variances that are yoked together. And then in the scalar model, once we pick up labels on the intercepts in the alternative group, we simultaneously free the factor mean in the alternative group. So constraints on the intercepts go with factor mean being estimated in the alternative group. Factor mean is still fixed to 0 for identification in the reference group, and the factor variance is still fixed to 1 for identification in the reference group. Okay, did that help, Jordan? Maybe.
I can just talk. Yeah, no, that helped. I was just confused because in the homework, it asks about freeing up the factor variance and the factor mean in the configural model section. So I wasn't sure if there'd be a different step you'd need to take to free it up at that stage and not using kind of the next step in the graded response.
In the configural model, the only way that they would be free is if the model was identified such that the loading, one of the loadings was fixed to 1. That's an alternative way of setting up a configural model, but that's not the way that I generally recommend. Okay, other questions on invariant stuff? Not yet? That's fine. It's early, but that way you can move as quickly through this stuff and finish your semester as you'd like. Not due until the end of finals week, though. All right, what were we talking about last time? Here, look at something prettier. What do you remember from last class? Higher order factors? Yeah, what are they for? What purpose do they serve? You know, I gotta tell you guys, when we get back to a regular classroom and I can sit and physically see all of you, I am gonna be so much better at handling awkward silences after this extensive training where no one talks to me when I ask a question. I'll be like, "I'll wait. It's fine. I will be as patient as it takes." There we go. Yeah, higher order factors, what are they for? They account for the covariances among lower order factors. Yeah, so up to this point, we've just been calling things factors. Now we need adjectives to distinguish what kind they are. So the original factors, when you have 3 or more of them in a model, you might want to have them be indicators of a higher order factor whose job is to predict their covariances. Yeah. When there is a higher order latent trait that accounts for much of the covariance between the factors. Yeah, that's what it's for. So a logical prerequisite to having a higher order factor is having covariances among the lower order factors. So Andrea, for instance, you have a 2-factor model in which the factors are basically uncorrelated, right? I do not envision a higher order factor in your future. So whether you think that would be theoretically useful, game over for that, because there is no correlation between them. We talked about strategy for higher order factors, and I was giving Jordan a hard time about his internalizing, externalizing, and so forth. I didn't mean to give you a hard time, Jordan. I just thought it was a good example. So even if you have lower order factors that are correlated, it may not be helpful to have a higher order factor sometimes. So whether or not it's a good idea depends on what you want to do with it. So do you remember when it might be a useful thing to have a higher order factor, providing that you have covariances that would support it? In what situation is a higher order factor useful? One answer, to prevent collinearity. Yes. Keep talking. When would collinearity be potentially a problem? If you want to do something with your lower order factors, yes, also true. So we would worry about collinearity among the lower order factors. That word, by the way. So if factors are correlated, we could call those factor covariances when we want them to be correlated, and we call them collinearity when we don't, right? But those are the same idea. Collinearity is a problem amongst predictors in models, right? Collinearity makes it harder for us to determine the unique effect of a predictor versus what it has in common. So yeah, if you are envisioning your lower order factors, let's say internalizing, externalizing, and avoidant, what was it? Antisocial behavior, that's what it was. If we're envisioning those as predictors of some sort of developmental outcome, high school graduation rates, subsequent substance abuse problems, stuff like that, right? To the extent that those three variables are highly related, it's going to be very difficult to see to what extent they each contribute to predicting those eventual outcomes. A way around that problem is to fit a higher order factor that would represent what they have in common, and then that common part goes and predicts the outcomes. So it makes the collinearity work in your favor because the common part then is what becomes the model predictor. So when would it not be helpful then? When it's the thing you want to predict, when they are only outcomes? Yeah. So if the factors are the outcomes, you have a bunch of covariates, let's say, or other sorts of predictor variables that are separately measured, and you want to know how each predictor relates to internalizing, to externalizing, to antisocial behavior, lumping them together into a higher order factor would obscure that relationship. I can give you an example. Would you like to hear a quick story? Why not, right? Who wants to talk about statistics? Let's talk about stories. But it is a story about statistics, actually, and it's a true story. So, once upon a time, when I was a graduate student at KU, this story happened in about the year 2003, so it's been a while. We got a new methodologist who started working at KU my last semester there. And this person worked in the same research unit in the Lifespan Institute that I had a GRA appointment in. And he invited himself onto my dissertation committee. I know. So I had 6 people on my dissertation committee. Scheduling that meeting was non-trivial, let me tell you, but I did eventually get it scheduled. And you're going to hear about my dissertation because it is example 9 that we have to talk about when we get to structural equation models, which we're sort of already doing. And back in the day, I used to study cognitive psychology and aging, adult development, and the focus of my dissertation was predicting impairment in a driving simulator in older adults from age, visual impairment, and attentional difficulties. And the whole point of my dissertation was to develop a new measure that tapped a different aspect of attention than other measures that were out there. It measured the efficiency with which one can do a selective attentional search task. So in the model, the whole point of it was to pit my new measure against these other related measures to see to what extent my new baby that I lovingly created and crafted and fit an IRT model to that fit badly and had no information to it, but whatever, that new baby was going to predict simulator driving impairment, right? That was my research question. Fast forward to my defense, and said new committee member points out that my attention measures are correlated. Well, yeah, there are three ways of looking at the same underlying physiological process. So, yeah, they're probably going to be related, but they each sort of measure distinct aspects of it. And I wanted to see the relationship of each of them uniquely to my outcome. And we got into an argument during my dissertation defense because he insisted that those three measures of attention needed to be indicators of a latent factor, and the latent factor had to predict driving impairment. And I was like, that's not my question, dude. I can't tell what the unique effect is of each predictor if you bundle it up into a higher order factor and then have that factor predict the outcome. I can't answer my question. So I don't care if my measures are correlated if I can't answer my question. And we went round and round for like 10 minutes about this. And I was just like, dude, if you're going to announce to the rest of the committee that you didn't read any of it, like, seriously, like at least read the research questions before you start arguing with me about my methodology. And eventually my chair cut off the discussion and was like, okay, we need to move on. But yeah, so when ending up publishing this work though, I did present that as an alternative model in the publication, and that is the model that I actually have to show you next week, the one that he wanted, even though it didn't actually address my question. So I guess I should begrudgingly thank him for suggesting that idea as reviewer 3. But you know what the moral of the story is? I wrote it up, I graduated, and I'm here to tell the other side. That's the moral of the story. The other moral of the story is just because you can do something with your data doesn't mean it's a good idea. Just because things are correlated, making them into a factor may or may not actually help you understand the relationships that you're focusing on. So there's a lot of gray area in when these things can work. That's what we talked about last time. And then we started looking at an example. Do you remember the example? 5 ways of being shitty to your kid? That's the latent trait of interest. All right. Any other things you want to talk about before we dump back into the example? All right, let's look at that then. So we are doing the same analysis 2 different ways so that I can give you an example of what it would look like in a CFA linear model framework versus an IFA IRT nonlinear model framework, because surprisingly, it turns out to be pretty much the same, because at the level of the lower and higher order factors, all of those are supposed to be continuous. So the distinctions between the measurement model don't really matter when it comes to testing the higher order model. So this is page 4 of example 8. We are looking at, to start with, a 5-factor model. So in this specification, it's like we've dumped in all 5 factors simultaneously. The model is identified such that all of the loadings are being estimated, which means that the factor variances have to be fixed to 1 for the model to be identified. And all of the intercepts are also being estimated. You can't tell that from the code, but that's a default in the model, which means that all the factor means have to be fixed to 0, which is also a default. And then last but not least, I am just allowing all 5 factors to covary. So I'm looking at this as the best fitting structural model I could have. This is the equivalent of the H1 when it comes to the factors. Each factor gets its own variance, each pair of factors gets its own covariance, and this is as good as it gets. So this is my baseline against which to compare the fit of a higher order factor model to see if it can account for these covariances. So we look at the fit of it, and this little table here, these are the correlations between the latent factors. This shows up like this in a matrix format in Tech 4. So add tech4 to your output line if you want this matrix. Otherwise, it's listed as a series of with statements and you have to build the matrix yourself. And I asked last time, does this look like it's consistent with a higher order factor? And the answer was mostly. They're definitely highly correlated. So if I were to put these 5 variables, latent variables, in as predictors, it would be difficult to ascertain their unique effects. And some of them are more correlated than others. So spurning and terrorizing are basically the same thing, whereas the ones that have to do with corrupting are of a lower correlation. So corrupting is more like a parent being a bad influence or being sort of lazy as opposed to being actively shitty. So that's a different breed of damage you can do to your child. So we fit a higher order factor model by changing the method of identification in the lower order factors. So note the change to the measurement model. The first loading for each factor is fixed to 1. Now, why did I do that? Why did I have to change from having the factor variances fixed to 1 to having one of the loadings fixed to 1 instead? I needed to estimate the factor variances, yes, because they become leftover. Yeah, they become disturbances. Disturbance is the term for factor variance left over after being predicted by other things. And so they have to become quantities that are unknown. That is why. So by fixing the first item to 1, we can then estimate all the factor variances. Quick question, does it matter if it's the first item fixed to 1 versus the second or the third or whatever? Correct. Nope, don't matter at all. The only situation in which it matters is if you happen to pick an indicator that has 0 relationship with the trait, because then it doesn't have any variance to force up to the trait level. I have actually seen that happen, and the way that we figured it out is the model would not run. Like it looked like it should be fine, and it kept coming up with like, I can't figure this out. And it will tell you it's not identified, and you'll know that it broke if all you get is a column of estimates and you don't get a column of standard errors or anything else. That means it's broken. And I couldn't figure out why it was broken, and so on a whim, I just picked another item, and lo and behold, it went fine. And it turns out that item that we had used as the marker had a factor loading that was functionally 0. And that was why it broke. That's the only situation in which it matters. So because we now have my factor variances estimated, they'll become leftover variances. And I know that because of the extra line I put right here. So I have created a higher order factor named abuse, and its items, so to speak, its indicators, are the lower order factor names. So order of operations in writing your code matters. M+ would not know what this line means until you've defined what each of these words means. So like you have to have it know what the lower order factor of spurning is before you can then use that as an indicator. So just keep that in mind to sort of build from the lowest level of the model, items to lower order factors first, then lower to higher. That way the order of operation stays okay. The loadings of the higher order factor to the lower order factors then are all estimated, and the higher order factor is identified by fixing its mean to 0 and its variance of 1. And what's not in the code at this point that was in the previous model? In addition to changing the way that the lower order factors were identified, I also took something out. Yeah, the lower order covariances. What would have happened if I left them in? double-barreled. Yeah, it would M plus like it? it? It would not be happy. It would not be happy. It would yell at me in capital letters. I don't know if you guys have seen your output has any error messages in it. It yells at you in capital letters when there's error messages. But yeah, the factor covariances are supposed to be replaced by the higher order factor loadings. So they'd be redundant. The model would not be identified. So we then looked at the fit. I did a likelihood ratio test comparing the fit of the previous model that had all 10 factor covariances against this model that replaced them with 5 higher order factor loadings for a savings of 5 parameters. The difference is significant, and this is where we left off, right? So significance in this case is good or bad? We have a vote for good. If I want there to be a higher order factor of abuse, is it good? Yeah, not if I want my higher order factor. Yeah. So I don't have evidence that a higher order factor is sufficient to represent the lower order covariances. So now I got to figure out why. So here are the loadings. It looks like all of the lower order factors have a strong relationship to the higher order factor. So it's not like any of them are bum items, so to speak. So now we need to go into the pattern specifically to see where the misprediction is. And this is something that I do not think M plus will do for you in the same way that you can look at the misprediction at the item level. So local fit is what we're talking about. Previously, when you did local fit in CFA, you looked at the normalized residuals, right? Remember those? They are z-score-like indices of how far off the covariance predicted between two items is relative to the real one, where positive values mean that they're actually more related than predicted and negative values mean they're less related. And M plus builds the matrix that does that for you. In WLSMV, it does the same thing, but not in a z-score metric, just literally how far apart the covariances are, the correlations. I'm going to build that because M plus does not do that at the structural level. But what I'm talking about is diagnosing local misfit amongst the higher order to lower order factors, the structural part of the model. So here is how I'm going to do this. The first block of colored correlations here, those came from the 5-factor model with all possible covariances, the perfect model with respect to the structural model. The one underneath it is the one that was predicted by the current model. I got that out of M+. That comes out of TECT 4. Model Estimated Correlation Matrix is what it's called. So the top matrix came from the previous model, the middle matrix came from the current model, and literally one minus the other is what this next little table is giving us. So there are two in particular that look to be bigger than any of the others. The model is missing a relationship between terrorizing and corrupting that is stronger than what the higher order factor predicts, and terrorizing versus ignoring is weaker than what the model predicts. And so lo and behold, if I go over to my Voodoo, modification indices available anytime you've got a covariance matrix as your answer key, that's what it wants. So it wants, the last column gives you the standardized version of the exchange of the parameter that you would be adding. So it wants a residual correlation, I guess it'd be a disturbance correlation between the lower order factors. And if I did that, the chi-square would improve by 44. It also wants a negative residual correlation between ignoring and terrorizing. And so these patterns is what these modification indices are picking up on. So in this case, because there's really only two that look to be problematic, and they're not that problematic, I would say that we can work with the higher order factor and add these things in. If I ended up with a matrix in which like there was a whole bunch of problems, then I might have to think about maybe two higher order factors instead. So you can have more than one. With five indicators, I think two is the most that you could probably have without it being unidentified. But this fit was not super horrible. Like it's within striking distance because this is how far off the predicted correlations are. So I added that additional relationship. Those two lines are what make this next model different. So the with statement in this case is between the lower order factors, and M+ understands that because these lower order factors are indicators of a higher order factor, that I'm actually referring to a covariance with their disturbances as opposed to their original variances. Okay, with me? All right, let's see if it worked. So I did two different likelihood ratio tests. First, did adding those two things help? So that's a change of 2 relative to the model that just has the higher order factor. And yes, chi-square improved significantly. So adding those two residual relationships significantly improved the fit of the structural model. And then, is it good enough yet? That's the second model comparison. So this is the current model relative to the perfect, all the factors get to be covariate structural model. So I have estimated 5 loadings and 2 disturbance covariances, which is 3 fewer parameters than all possible. So relative to that, it's non-significantly worse, so I win. So I have a higher order factor, except that there is more of a relationship between corrupting and terrorizing than what the model predicts, and there is a negative relationship between ignorizing and terrorizing. But otherwise, this looks like a pretty decent higher order factor to me. And as always, words. So a happy ending to the story of 5 ways to be shitty to your child. Questions on that?
I have a question that kind of goes back to the big picture of the factor structure.
Mhm.
So if I'm understanding this right, the loadings for the lower order factors represent the amount of variance that is common with the higher factor
Yes.
and those items that are in that lower order factor, right?
Yes.
So when we talk about so the positive covariance between lower order factors makes sense because it'd be like extra common variance.
Mhm.
But the negative one is a little bit confusing to me because I'm trying to think about it's like common variance that goes through that higher order factor. But could you explain that a little bit, like the theoretical idea behind that?
So yeah, if you picture like the structure sort of trickling down to the items, like the higher order factor at the top does predict a correlation between it and each of the lowers, and then the lower goes down to the items. And so all of the items are predicted to have correlation across this entire 49 items. The ones that are from the same sub-factor have a stronger correlation, but they all have a correlation if you trace all the way down. This negative relationship here means that whatever not the factor is, so the disturbances, like whatever is not abuse, has a negative relationship.
Whatever is, oh, okay. I thought you maybe were gonna say whatever is not ignored but is abuse.
No, abuse is already predicted it. This is the leftover part.
Okay.
And so, as an armchair psychologist here, I'm just going to make some shit up and say that this is theoretically plausible because it has to do with effort.
Yeah, like you were saying.
Like ignoring your child is the easiest thing that you can do. Actively terrorizing your child takes effort. So people who do one are probably less likely to do the other. But there's a common enough that's in common that we have evidence that this looks like these are all sort of flavors of one idea. Corrupting is less related to these things, and it looks like the other ones are all pretty much the same. Um, let's see, what if I wanted to address a question about whether or not corrupting is significantly less related to the higher order trait than the others? Could I do that? You think of a strategy? Because it kind of looks like spurning, terrorizing, and isolating are all about the same, and corrupting is a little different. So how would I test if the loadings differ? Have I made you do this like 17 times? Yeah, constrain them. Constrain them equal and check the change in the fit. So all kinds of hypotheses can be addressed by patterns of constraints in these models. I would be careful about making statements that are comparisons without a test to back it up. Like I would not write in my results section, at least I hope I didn't write, that spurning is more related to the trait than terrorizing, right? Just based on these two numbers, because I don't have a test that backs that claim up. I should at least put in some hedgy language if I'm going to say that, like appears to be more related. Appears is academic for I'm going to make some shit up now. Is that all right with you? But never make shit up when you can provide a hypothesis test. That's a personal motto.
So just to clarify, you would just constrain the other four factors to be the same, or you would
Yeah, it
add a
depends.
covariance and then constrain that.
I would not add a covariance, but I would set up a pattern of constraints that would isolate corrupting from the others probably. Like if I wanted to say that corrupting was less related than the others, that wording sort of implies then the others is lumped together. Versus if I wanted to say corrupting is less related than spurning, then I just focus on like setting those two equal as opposed to being unequal.
Gotcha.
All right, so this is how it works in the world of CFA. It works remarkably similarly in the world of WLSMB. The only difference is having to use diff test to do your model comparisons, which means that you have to change the order in which you estimate the models. So the one that has the most parameters has to come first. The one that is a reduced, more parsimonious model has to come second. So in the world of WLSMB, I am starting with the 5-factor model rather than the 1-factor model as the highest. The only difference in the code is denoting them as categorical and changing your estimation method over to WLSMB. Literally the rest of the code is exactly the same. I'm going to be saving the results of this model on using diff test so that I can compare it to the next model. So the 5-factor model fits pretty well, although CFI and TLI are not slightly less happy with it. That was the same pattern we saw before. Here is the single-factor model as a first point of comparison. And I cheated that the same way with fixing all of the factor covariances to 1. I then asked for the comparison against the 5-factor model. So I get my chi-square for difference testing. So this hypothesis test right here that I have highlighted, what that is testing is whether or not the 10 covariances between my 5 factors can all be fixed equal to 1. And it looks like no, that is a bad idea. So there's not a perfect pattern of covariance, which means I don't have just one factor. It is 5. And here is the higher order factor model, which I am going to compare back to the 5-factor model. Here's my significance test for that. Did the 5 higher order loadings do a good enough job for my 10 covariances? Sadly, no. Go through the same process of trying to figure out where the problems are. Compare the pattern of correlation from the saturated model to the one that's predicted by the current model. Look at where the differences are. Same exact tendency, where terrorizing and corrupting are positively related, terrorizing and ignoring are negatively related. Gonna add those 2 disturbance covariances, see if that makes it better. And Word has apparently lost its mind. I don't think it's supposed to look like that. It's very interesting. Well, I do have words here, but you'd have to be very talented to read them. Fortunately, I remember what the story is. And actually, the story is just this right here that I can see. Nah, not quite good enough. Heartbreaking, still significantly worse. So I'd have to go figure out what else I want to add. And I was like, nah, I'm done with this handout. It's enough. It's fine. So point of the story, once you have your measurement model set up, all of these activities involving the structural model and what should go in it are the same, regardless of whether you have a ordinal factor model or a confirmatory factor model underlying your item responses. So Jing says the PDF you downloaded is okay. Well, thank goodness, because that may be the only version here. I don't know what's up with this, but who knows? It's 2020. Anything could happen. Maybe the murder hornets got into it and started chewing. Who knows? They'll go nicely with the mice that are living in my basement. For reals. Yeah, we have a mice infestation in our basement. It's fun. You can hear them crawling in the walls. So, yeah, the E.F. Lindquist chair is also currently playing Exterminator at our house. He's in charge of setting the traps and throwing out the dead rodents each morning. So, good times. Yeah, time to get a cat. No kidding. Except I really don't want the cat to bring me a dead mouse and be like, look, Mom, look what I did. Because I know they do that. And no. So, yeah, it's 2020. What can I say? All right, let me get rid of this thing. Questions on that? Because I've got some more stuff to talk about if not. Yeah, I doubt the mice are going to come out during the daytime, but if I ever start screaming uncontrollably while I'm teaching, that's why, because I am teaching from my basement. So, all right, what did I want to find? I wanted to find this thing. Let me go back to some other higher order examples. So I have some examples of other ideas people have come up with to save factor structures that didn't fit like they wanted them to. So open in case of emergency ideas here. This is slide 10. So the world of method factors, by factors, and other fun stuff like that. So this is an article that's on your reference list, I believe, exploring different ways of measuring and capturing sort of valence-specific variance having to do with wording. So here are a set of items that are all supposed to be measuring one thing in common, except that some of them are worded positively, 3 of them, and 4 of them are worded negatively. So whether or not you're optimistic. This is a scale that's supposed to assess optimism. If we look at the correlations, some of them are negative, as one might expect, but if we flip them into a reverse coding, it does look like there's some evidence for something in common here, right? This looks like we could work with that. So they presented a series of alternatives for these type of data. So first, they fit a single order factor. So the code would look like this. Optimism as a factor is indicated by the 9 loadings. Fix the variance to 1, fix the mean to 0, and that didn't work well. And it looked like the problem was that the items that were worded the same way wanted to go more together than items that were worded differently. That's a very common thing that happens when people decide to reverse code some items and not others. So the easiest way to fix that, and the way that I demonstrated in example 4, was to just have 2 factors, one for each. And in this case, they did not reverse code their items, and so they were negatively correlated. So we have a factor for optimism and a factor for pessimism. And so that would look like that. But this is dissatisfying if what you really want to measure is the one thing that they have in common and just sort of like shove the wording problems under the rug, right? Like that's extraneous variance. I don't want to talk about it. I'm going to fix it. So here's some ideas on how to fix it. So this structure right here, this has a bunch of different names. It's known as a bifactor model in the IRT literature. It's known as method factors or specific factors in the CFA literature. But the idea is taking what would have been residual covariances and putting them into the model as factors instead. That's the idea. So in homework 5, those of you who had added residual covariances under your CFA model found that you couldn't do that when you were estimating your IRT model with full information, but you can do this trick instead. So this is a generalization of the trick that I showed you by which you can put in a factor, fix both loadings to 1 and estimate its variance and call that your residual covariance. So the way that they've done this here is that all of the items load on what is supposed to be the trait. And then we have these specific factors, as they're known, that are supposed to capture the extraneous variance that's in common, but that's not the trait. So what they're trying to do is take what we used to just call not the factor and further subdivide that into not the factor because of how it's worded, which is specific optimism, and then not the factor because it's worded the other way. And this is a reasonable structure to impose. However, it falls apart. So the problem with this is that we end up with loadings on the specific factors that are higher than the ones on the general factor. So even if this fits well, looking at the patterns of factor loadings, the wording factor, for instance, on the first item has a stronger loading than the content. So that might cause someone to say, okay, now which of these is the content and which of these is the control? Because that interpretation depends on having the pattern of loadings shake out to support it. The ones for the pessimism factor, actually, they look to be non-significant, indicating that they are not even needed. There's too many loadings in here. So the solution that they settled on is something that he called a random intercept factor. For those of you who've had the clustered multi-level class, this is the same random intercept thing that we talked about in that class. It's the idea of inducing a constant covariance. And so they fixed all of the loadings onto this random intercept factor to 1. So what this does then is force all of the items that are worded the same way, or in this case, not all of them, all the items, period, just to have an extra source of constant covariance. And because this fit reasonably well, they interpreted this as some kind of response shift. I think that's a bit of a stretch, to be honest, but at least this is a factor structure that is theoretically useful in that we don't have too many factor loadings competing as to which is the trait, which is the method. We do have something that's soaking up extra covariance that you don't want to necessarily represent. We still have our single trait. And so they went and said, look at this as an idea. So there's all kinds of crazy things you can do with factors that allow you to try and represent multidimensionality in a way that is a little bit more palatable than just sticking a whole bunch of residual covariances in your model. Kelly is confused. So the random intercept is like a leftover, but it was actually more impactful than the real factor. In this case, no. They're estimating a variance. What this is doing is just allowing a constant source of covariance between the items, and then this one picks up different loadings across items. And so in theory, the scaling of this is confusing because it's not really more in the fact that it's one. This one's just identified differently. They could have fixed the variance of this to 1 and then pick a common loading across all of these, and that would have been put them on the same scale. The idea is that whatever they are having, that they're being measured with the trait, that gets to shine through over here, and this just sort of soaks up extra correlation that's not the trait. The pattern of loadings would have to support it, which in this case, they're all nice and strong, which seems like that's a reasonable interpretation. So it's not without some criticism. It gets a little squishy. Here's an example from my life, the Heartland forgiveness scale. So this one is supposed to be 3 factors, measures of the extent to which you can forgive yourself, the extent to which you can forgive others, and forgive a situation. We looked at situation forgiveness in example 4. Do you remember that? It was like 3 months ago, so it's okay if you don't, but it was a while. And what we found in that case is that a 2-factor model, where the 3 items that were worded about positively worded, meaning forgiveness, were more related to each other than the 3 items that were worded to convey unforgiveness or grudge holding. And that turned out to be the case in the other subscales as well. So the best fitting sort of structural model would look something like this, where, by the way, this trick with the arrows that are connecting to each other, that is a cheat to convey the idea that all 6 factors are correlated. So if you were to draw all of the covariances among the factors, that makes the diagram very clunky. So I like this as a way to represent that idea, but to keep the diagram looking a little bit simpler. So this is a model that I was like, okay, what do I do with this? Because I want to measure forgiveness, and I've got 6 of them, but I've got 2 for each kind, but then I've got wording factors, and is that just a problem, or what do I do with this? And so this was the solution that I had to solve, and eventually came up with this thing. So this is what's published in the Heartland Forgiveness Scale article. This represented the best I could do in 2004. I don't know if I would have come up with the same thing again, but it actually fits pretty well, and I tried it on some of their other data sets, and it held together. People who have translated the scale into other languages and given it to other cultures came back to us and said they're finding different structures. And I'm not at all surprised by that, because the extent to which someone who holds grudges is the opposite of someone who's forgiving may differ as a function of how you've worded the questions and that kind of stuff too. But this is the crazy ass factor structure I came up with, okay? So I've got higher order factors of self, others, and situations, because that's the way they wanted to talk about this. I constrained the loadings for the positive factors for each to be equal to each other, and I constrained the loadings for the negatives to be equal to each other too. Now that is not just something that I chose to do, that's something that I had to do. Can you guess why? Why would I need some pattern of constraints over here for these higher order factors? How many indicators do I have of each higher order factor on the right-hand side? 2. Is 2 enough? No. So I've got to constrain the loadings somehow. My choices were to constrain them each equal to each other within a factor, and that actually didn't work. It did not work well. So what I ended up doing instead is this pattern of constraints that has the side effect of not only making the model identified, but also making it so the extent to which the positive items contribute and the extent to which the negative items contribute is the same across all three factors. So it sort of prevents a confounding of content variance and method variance, because you wouldn't want your self items to be more of the positive than the negative, whereas your other items are more the negative than the positive, right? That complicates the interpretation. So that side then makes this identified, but in a way that makes it sort of more palatable. Okay, with me so far on the right-hand side? Now, even after controlling for what the items are supposed to be measuring, how they measured it was another source of covariance that I had to soak up on the left-hand side. And so these are my so-called specific factors or methods factors that induce a positive correlation amongst the sub-factors that are measured from the same perspective. And I was able to constrain all 6 loadings to be equal to each other to support the idea that it is just a wording thing and not a trait thing. If I had different patterns of loadings onto those positive and negative factors for the different contents, then it would make a harder argument as to separate out what is content from what is method. So this facilitates an interpretation that it really doesn't matter what the item was asking about, it's just the wording. They all are equally related to their wording traits. And I was able to constrain the disturbances to be equal to each other so that the same amount of not the factor variance is obtained for the positively worded items as for the negatively worded items. So it's a whole slew of constraints that makes it so that we can talk about self, other, and situation pulled apart from all of the wording variance as much as possible. Isn't this a thing of beauty? I was super proud of this. Do you know what everybody does in life with these items now? Can you guess? Do you think they fit this? What do they do? I bet you can guess. Add them all up. Yep, we're just going to add this shit up. It's fine. Add up the 18 items. We're going to call that forgiveness. Job done. That's what happens. So, you do what you can. But I learned a lot in trying to make this structure work. I also had to fight with a reviewer about it. One of the reviewers wanted to say that no, the right-hand side are the method factors, and what you've really measured are overall traits of forgiveness and unforgiveness. And you've measured forgiveness and unforgiveness in 3 ways. So over here are your contents, and over on the right side are your methods. Reviewer 3 wanted me to defend that, and I did. Didn't have that on here. What I ended up doing is reversing the patterns of constraints. So forcing it to look like these are measuring the traits and these are measuring the methods, and it didn't fit as well, and so I got to say, suck it, reviewer 3. My factor structure is better. I'm not measuring forgiveness and unforgiveness. I'm measuring self, others, and situations, damn it. Just doing it with positively and negatively worded items. So there's all kinds of possibilities of how you can collect common pieces of variance and put it into a factor structure. All different kinds. And I would encourage you when you're doing that to use constraints that help reinforce the definition of what the factor means. If something truly is just about the wording, then the loadings should be able to be the same regardless of what it's measuring, because it should just be the wording. So that helps bolster your interpretation as to what it actually means. All right, here's some stuff that's going to make your head hurt. Which way the arrows go. Doesn't really matter. So people sometimes refer to structural equation modeling as causal modeling. Have you heard that phrase before? That should make your skin crawl because there's no cause without design, right? I have a covariance matrix and I'm going to parse it up in a bunch of different ways. There's no causality there. So if I have a path model, which is just relationships among observed variables that looks like this, that fits mathematically equivalently to a path model that looks like this. They are both over-identified with 1 degree of freedom because both models do not include a direct relationship between A and C. But each model does include a direct relationship between A and B and C. And so from a fit statistic perspective, they are equivalent, even if they make very different statements about what is driving what. So another story, true story, in which I was on a dissertation committee, and a student had a model that was a hell of a lot more complicated, but the structural part boiled down to this. It was a mediator model where there was X to M to Y to fit the triangle. We'll talk about that next week. And so this student has a personality that is very much like not arguing, conflict avoiding, like very passive person. And another member of his committee starts talking and is like, well, I think that your X should actually be your M and your M should be your X and the arrows need to go the other way. And did you see if that fit better? And so I'm looking at the student going, yep, you know the answer to this, go for it. And he can't bring himself to like, I guess I should try that. Yes, I'll write that down and try that. And I'm like, nope, ain't gonna fit better. If all of the paths are in there, it doesn't care which way they go. So no, I had to shut that down. That is a common thing that reviewers will be like, is the model, I think you fit the wrong model. I think the paths go a different way. Does it fit better if you try it my way? In several cases like this, the answer is going to be no, because it's an equivalent model. There was one time where I could definitively say that I had the paths in the right order. Another story. The follow-up to my dissertation was we called up the participants 5 years later and asked, oh, by the way, have you crashed anything lately since you came to the hospital and did my dissertation driving study? And some of them had. So we use the information in my dissertation to predict accidents and speeding tickets 5 years later, and I found that the measures of driving impairment actually did predict that, and so that became a nice little follow-up paper. And one of the reviewers questioned the direction of the paths. And I was like, nope, I got this. Well, because this happened 5 years later, I'm pretty sure I've got the arrows right. Unless you can tell me that I can bend the space-time continuum with the right option in M+, in which case maybe I could have the future predict the past, but I don't think that's usually possible. So I was like, that time, that's the one time. Otherwise, if all of these items or variables are collected simultaneously, which way the paths go, it's not something that you can say definitively that you're right. Question, what about if there's a time difference between variables? Is there any possibility of causal interpretation? Oh, I think you're asking me if the data are longitudinal, then can we see that we have the arrows going the right way? Longitudinal data, when analyzed properly, I think can get you further over on the causality spectrum because you can control for stable individual differences and then see what happens within a person, what determines their changes over time. So it's more causal, but unless the design supports causality, then the answer is still no. because you can watch people age, right? You can watch children grow up, you can watch old people deteriorate, but you can't randomly assign age. And so there's really no way to say definitively that it's the developmental process that's responsible for something. And if I can put in a plug for next semester when I say learning how to analyze longitudinal data properly, your chance to do that is coming up in spring 2021. Come hang out with me again on the Zoom every Tuesday, Thursday afternoon. The class has 22 people in it, so it's getting filled up. If anyone wants to come, sign up now. We'll talk about longitudinal models, and a lot of this stuff will sound familiar, even though it sounds a little bit different from that perspective. So anyway, beware equivalent models. This picture is even more disturbing, I think, in terms of what are equivalent models. So this picture is from your textbook. The diagram on the top left says that D1 is a predictor and that it predicts a latent factor of depression, which is measured by items 2, 3, and 4. The picture on the right just says, no, D1 is a measure of depression. What are you talking about? And the picture down here is like, no, it's D3 that's the cause, and D1 is the measure. And guess what? They all fit the same. Because if we go through and figure out the pattern of predicted relationships, they all are predicted to have the same pattern with all three of these pictures. So it's really like when you put it from this perspective, it's like, whoa. Like that is a different way of looking at the same set of 4 items, but the math can't separate out which of these is correct. You could potentially go down the road of figuring out which is more correct if you had other stuff to relate it to, and if you could constrain certain relationships to be part of the model versus not part of the model and watch changes in fit, you could start to sort of figure some of that out. But ultimately, yeah, beware equivalent models is the take home. We don't necessarily know what the truth is. So thanks for coming to my TED Talk. That's the perils of equivalent models. There's a lot of work on this, by the way, and it's scary. Generally speaking, the more parameters in your model, the fewer degrees of freedom, the more equivalent models are out there that would fit the same, even if they say very different things about the same data set. So this is not causal modeling. All right, any questions? So for next week, I have put up, let me pull up, let's see. I have been logged out. Well, thank you for that. I have put up some extra stuff. So I have 2 examples from a previous course. Those of you who are with me in the Generalized Linear Models course, where we did path analysis, I have 2 examples of what is called path analysis, which is fitting models like the ones that we were just looking at that have nothing to do with latent variables. For whatever reason, in a structural modeling course, path analysis is often taught at the same time, even though it's just regression and has nothing to do with measurement. So I've deliberately decided not to put these examples in this course so that we can spend more time looking at path models that have latent variables, which is SEM. So if you've never seen path modeling before, it would be a good idea to check out these examples. I'm guessing that you probably don't need to listen to all the videos. You can just sort of look at the code and see what's happening in the results and make sure that you can follow it. And that may make it a little bit easier to go through the SEM examples next week. So just a heads up, if you haven't seen this before, there's some extra material to look at. All right. Anything else? Ready to call it a day? Why not? All right, 5 whole minutes early. How nice am I? All right, office hours start now if anybody wants to hang out. Otherwise, stay safe. Have a good weekend. See you next week.